Good. So yesterday we talked a bit about polyhedral geometry, generating functions of lattice points in simplicial cones. And now I will go to some tricks, so hand-picked tricks from polyhedral geometry that we will need in order to see the geometric version of an analytic method related to partitions. So, yeah. So from yesterday, if we have a cone, let's say generated by G1 to GD, simplicial cone, then we said that the rational generating function of this is the product of 1 minus z to the g, let's say gi for 1 to d, and here we had the generating function for the fundamental parallelepiped of the cone. Okay? So, by the way, one question could be, what about non-simplicial cones? The answer there is, there are two possible answers. One is that we can all take any cone and make it simplicial by triangulating. But I don't want to go into details about that, because actually, in whatever I will talk about later, we will stay by construction, due to what McMahon did, we will only stay simplicial. So we'll not need anything that is not simplicial. Okay, now, so let's take the real line, right? And let's take this ray here, where we have lattice points there. So, what is the so this is a cone. It's actually a simplicial cone, right? It's the cone generated by 1, 0. By 1, actually. Very one-dimensional, right? So it's a ray going from 0 to infinity. What is the generating function for that? For the lattice points on this ray?
1 over 1 minus c.
Yeah. Right? So, and according to, we had this discussion yesterday, obviously 0 is in the natural numbers. But anyway, so, okay, what about these points? So I can take this ray, right? Starting from -1 and going to minus infinity. What would be the generating function for these points? So this is the cone generated by -1.
C minus
1 over 1?
C minus 1.
Like this?
1 minus c inverse.
Again?
1 minus c inverse.
1 minus z where?
1 minus 1 minus c.
Wait, we're here, right? And plus what?
Not minus, between 1 and 0.
Read this?
Yeah.
Really? Yeah, maybe. But does this fit with that? I'm not sure. I mean, maybe, but so by the way, let me start using a different notation. So here we have the generators, and we also want the apex. And the apex is -1. That's a vector, right? And this one was 0. Anyway, I mean, if we follow this, right, this would be, the generator is -1, right? But we need to shift because this is the point when I said about cones, start the apex being at 0. We don't want it at 0. What we need to do is just shift everything, right? And we shift by -1. So shifting, according to what we discussed later yesterday when we were trying to do the generating function of the simplicial cone, shift means just multiply the generating function with the corresponding monomial, which would be z to the -1, right? So what we have is this, right? We agree? Is it what could be the okay. Now, how do they relate? Actually, what I will do here, let's see. If I pull out a z, be like that, right? And let me take this up, so it's like this, and then I have minus, right? Do we agree here? So my point is, if I take the whole line, obviously adding the two generating functions, right? So the two rays cover the whole line, right? If I need to find, now if I have two generating functions and I want to find the union of the objects they represent, I just add them, right? Okay, if I add these two, what do I get? So I get 0, right? This plus that is 0. So if a polyhedron contains a line, its a rational generating function is 0. Okay? Are we convinced? I mean, there are ways to prove this, which I don't want to go to. I mean, we have to do the proper setting. Otherwise, you can say it's a convention as well, right? So if it wasn't 0, this thing wouldn't work, for example, right? So, okay. This is a very important, obviously in the formal power series level, that's not true, right? We have a doubly infinite sum. But at the rational generating function level, this is 0. The generating function of anything that contains a line is 0.
Is that kind of like a degenerate case of sorts?
It's, I mean, it's not really degenerate, right? So actually, we will use it soon in order to. It's a very powerful tool, actually. So if you can introduce a line, you just get rid of whatever you had there, right? So before going there, let's see what happened here. We had a ray, right? Starting from 0 going to plus infinity. And if we flip the direction, we change the direction, so what else happened? So it was starting at 0, but now it is open at 0, right? I mean, we can say it starts at -1 or that it starts at 0, but excluding 0. So we change the openness. And also, we have to change the sign. We change nothing, right? So it's the same rational generating function if we do these operations. By the way, obviously, we can go back, right? So we take this, we flip the direction, we change the openness from open to closed, and we change the sign. Okay? So I will be flipping rays as needed, and we will see why this is needed. Okay. Now, our goal is to compute rational generating functions of polyhedra, right? And we only managed to do it for simplicial cones. That's a very small class of polyhedra. How do we go for more general polyhedra? So let's say we have this pentagon, and we want to compute the rational generating function for the lattice points in this polyhedron, in this polytope. How do we do this? Let's start with a plane, right? We have a plus for the whole space. And then, okay, I have to get this right. Wait. What do I have to remove? By the way, it's a fairly simple one. Yeah. Do we agree that if we take the whole plane and we subtract these 5 cones, what remains is our pentagon? Right?
Everything's not in.
Everything else, so this is half open, so we don't lose the boundary, but everything else is removed. Okay? Good. Now, let me take this cone and let me flip this ray. So, I'm allowed to flip, but then I have to change the openness. So this was here, open here, but now it will be closed. And I need to change the sign, right? Now it's a plus. 3 operations. And I can do this for all of them, right? So it will be exactly the same. The open part will become closed. The minus will be plus. And we will flip the one ray that was going in the other direction. Remember, this is at the level of rational generating functions, right? And what we have is that this pentagon, the rational generating function for the lattice points in this polytope, is equal to the sum of the rational generating functions of these 5 cones, right? Because we agreed that this is what we covered. No? So this is an example of Brion's theorem saying that the rational generating function of a polyhedron is equal to the sum of the rational generating functions of its vertex cones. Remember what a vertex cone is? It was the smallest cone whose apex is on a vertex of the polyhedron, the smallest cone that contains the polyhedron. So here, let me draw this again. Right, these 5 cones are exactly the 5 vertex cones of this pentagon. And Brion's theorem works in general, in any dimension, for any polyhedron, etc. If you take the vertex cones, take the rational generating function of these vertex cones, sum them over, what you get is the rational generating function of your polyhedron. So suddenly, we are fine, because we moved from any polyhedron to just needing the rational generating functions of cones, right? And we know how to do that. Worst case, you need to triangulate, but as I said, for us it will not be needed. Okay, questions until here? Sure.
So like, I can maybe see how the generating function that corresponds to a line itself would be 0, but then why is the whole polyhedron generating function 0? You know what I mean?
Well, one thing it would be that then you could split in 2 your polyhedron as a union of 2 things, a line and the other thing, and you would get a contradiction there, because if it wasn't 0, then the generating function of the line would not be 0. I know I'm not convincing you. So actually there is of course this is proven, and we need to go to evaluations. I think this is the most natural setting to prove this, but I don't want to go there. In principle, usually I say that this is magic, because that's how it looks to me. When I first saw it, it was like this. Now I know how it's proven, but it's still magic. And especially, yeah, exactly. By the way, here I didn't prove, of course, Brion's theorem. I just give an example. But a proof is based on the fact that take inclusion-exclusion for everything, right? So every dimension, whatever. And then, so you take all the face cones, which means not vertex cones only, but you would take also for this face, so everything like a half space here, etc. But, and we all agree that inclusion-exclusion works, right? It's fine. But then, everything that is not a vertex cone contains a line, and it disappears at the rational function level. Yeah?
So we all agree that the generating function of the whole plane, let's fix the dimension to 2, is 0. Yes?
I agree.
And we
take a cone, nice acute angle, and it has a non-zero generating function. Now think of its complement. The generating function is not zero anymore, but the thing contains lines.
Okay. Yeah.
How do we work around this?
It's like the sum of two non-zero generating functions can be zero, like in the example.
Yeah.
In the first example. Both sides are non-zero, but we get zero when we sum.
So, I will answer later. I will try to figure this out. I think it's related to what I'm about to say, because so I'm trying to avoid all the possible analytic arguments here. So the point is, one way to not like things that contain lines is because in the formal power series you have a double infinite sum, right? So in this, for people who use words like convergence and stuff, this is a no-go, right? So, but I don't want to make such an argument. So I will try to come up with a better one, or better for me. I think it's related to the next thing I want to say, which is intersections. So, let's take this ray, this polyhedron, right? And sorry. Let's take this segment. I have a segment, right? A one-dimensional polytope. And I have two ways to write it as a Brion decomposition, right? So I can say it is this minus that, right? I take this ray and I subtract this ray, but open there because of I need this point. Okay, let me start by what is the Brion? What are the vertex cones here? We have one vertex cone there and one vertex cone here, right? These are the, in one dimension, vertex cones will be just rays. I have two rays, one in each vertex. Now I'm just flipping this, so it becomes open, change the direction and the sign, right? Or I could just keep it like this, right? That's also fine. We know that this will give us the segment plus a line. The line goes away, the segment remains. So that we have many ways of decomposing this segment in terms of rays. Okay, and let's say now I want to take intersections. I introduce a new half space, and I take only the things that are in one side. So I will cut here, and I will keep things on the right of my new hyperplane. Okay, let's see what happens. My green line, and what I have is a plus, a minus, part of my segment, and here I have this, and I have a segment now, right? Because I cut here. Good? These are both pluses. Do we see something interesting? So this is actually fine, right? this plus that gives me the part of the segment that remains after the intersection, right? Here, no, I don't know what this is, right? So I cannot take intersections, I cannot cut my collection of rays or cones, my collection of vertex cones with a new hyperplane and have a consistent result in this second case. So what's the difference here? I want all the cones to look in the same direction, to look forward. I mean, forward is something you would define. It's arbitrary. You can take any direction to be considered forward. It would work if they all looked in this direction as well, right? So it's just that I want them yeah, so in 2 dimensions, they would have to be to look in this direction. In general, lexicographically sorted. So the first non-zero element should be a plus or a minus, depending on the choice, but a consistent one, right? So let's say that forward means the first non-zero element of the generators must be positive, which was not the case here. Good, but now if we flip, how do we make, can we always do that? Yeah, sure, we can always flip rays, right? So take any cone, we flip the rays that look in the wrong direction, and we get forward cones. We can always do that, and we may have to change signs or whatever, but it's always possible. And then we can take a Brion decomposition. Then we call it a Lorentz-Varshenko decomposition if it has this nice property, and we can take intersections. Okay? Questions? Good. Now let's go 100 years back, 100 plus something years back, and discuss about partition analysis. So this is a method introduced by Percy McMahon, and so he was interested in partition problems, and lots of partition problems, as I tried to convince you yesterday, and I hope I will manage until the end of the week, are essentially linear Diophantine systems, right? So Diophantine means we want non-negative integer solutions, and we have a linear system because that's the constraints we have for our partitions. So essentially, partition analysis is a method for solving linear Diophantine systems. And what do we mean by solving? Computing the rational generating function for the solution set of the linear Diophantine system. Good. Now, how do we do this? Let's say we have this linear system. Let's take an example. Okay, we have this, well, it's a small one, but still, dimensions. I cannot draw in very high dimensions. We have this linear system. How would McMahon solve it using partition analysis? So, first, let's take for every non-negative x and y, I want to keep track of them. Since I want non-negative integer solutions, right? I'm trying to write now the generating function. What is the constraint I want for this? They have to satisfy that thing, right? Okay, I will introduce a new variable, lambda, and I will put this inequality in the exponent. Well, I mean, that's that, right? And from here, I will apply the omega operator, which says what? Keep only terms with a non-negative lambda exponent. Then set lambda equal to 1. Okay? So if I keep only the things that have non-negative lambda exponents, right? What do I get? I get a sum over all x and y non-negative, z1 to the x, z2 to the y, right? But, well, not all of them, because they have to satisfy the inequality. So I sum over all solutions of the system, of the linear Diophantine system, and then I set lambda equal to 1, so I don't even need to put it there. So I have the generating function of the solutions. Do we agree? Right? So seems like very easy to solve linear Diophantine systems. Some problems. So first of all, those who understand complexity theory, it's not. So it's an NP hard problem. To decide if there is a solution is an NP complete problem, because yeah, it's a hard problem computationally. So obviously, these two simple arrows are hard to compute really. Some terminology, this is what McMahon calls the Crude generating function. And yeah, so then we have this omega operator that is doing exactly that. And in general, okay, so let's see. Can we write this as a rational function? Yes, we can. Or we can try at least. So in the numerator, I will have this lambda to the minus 5, because no x and y involved there. And if I take, okay, let me do it in 2 steps. For me, not for you. And right, so now we have lambda to the minus 5 over 1 minus lambda square z1, 1 minus lambda cube z2, right? As I promised, I will never use anything except for geometric series expansion. So that's a Crude generating function, the rational form of this. And the question is now, how do we apply the omega operator to get the rational generating function of the solution? Okay. Now, a small, how do you say? Okay. Here we go from something that contains a lambda to something that doesn't contain a lambda anymore. And in the process, we actually solve the system, right? So we want to introduce a variable and then eliminate it. And if here actually I had an actual system of many inequalities, I would just introduce more variables, right? And then I would just have more lambdas to eliminate, but nothing else changes. So the concept is the same. In lambda exponents. Okay, so I would only keep things where every lambda is non-negative. So all inequalities have to be satisfied. Okay, good. How do we do this? So what McMahon did is develop an algorithmic method, actually. It was based on Elliott's method. Elliott says the following. It says, if I have something of the form of this form, then this is what? Sorry?
Partial fraction becomes a
Exactly. Minus is it correct? I'm trying to translate back from the geometric picture I have, and I will give you in 1 minute, but I'm not sure if the analytic one is correct. So it should be correct. Yeah, so Elliott says that in order to solve one equation, what you need to do is that, right? So we start with something that has some, so two factors in the denominator where lambda appears with magnitudes alpha and beta, right? And then I will write it as a sum of other rational functions where either they will have one factor less, so clearly reducing complexity, or I will have again two factors, but one of the two will have smaller magnitude because alpha minus beta is smaller than alpha or beta, right? So, okay, and that's true for both of them. And he says that, you know, if you repeat this process, this is 1901, I think. He clearly says, if you repeat, you can repeat this process because the numerators, so what you get is of exactly the same form, right? He proves correctness of the algorithm in very modern terms, in some sense. You can continue this process until you reach lambda, the exponents of lambda to be 0. And when you reach the exponents of the lambda to be 0, you have the solutions to your equation. So he's claiming it for what we would say is omega equal. So if instead of inequalities we had equations, not much changes really. So this is Elliott's decomposition, which McMahon takes one step further, says, okay, we can have systems, blah, blah, blah. The only problem is that that's not something humans should compute by hand. Not even McMahon. McMahon was an insane computer, but even himself said, yeah, no, not really. So he introduced rules, so ad hoc rules, for specific forms of rational functions of this type that he would compute analytically the solution without using the algorithm. And this is a list that he was enhancing with when he would encounter a new form for a new partition problem he wanted to solve. Okay. Now, let me. No, that's bad. I'm trying not to go over time this time. So I have 7 minutes, right? So in the next 7 minutes, I want to go and see what is the geometry of this thing, right? So does this look like something we know? It's perfectly in the form of that, right? So all we need to know to prove is that the fundamental parallelepiped contains only one point, the origin, right? So this means that this cone, the cone defined here, is unimodular. If we have a unimodular form, you only have one term in the numerator because you have only one point in the fundamental parallelepiped. Okay, so let's see. Now I have to draw in 3D, my favorite. So why are we in 3D? Because we have Z1, we have Z2, and we have lambda, right? So, okay. What are the generators of this cone? So this is, we have one generator which is 1, 0, alpha, and a second generator which is 0, 1, minus beta, right? These are the generators. Is it unimodular, first of all? Yeah, sure is. Right, this is a generator matrix, and the determinant is 1. Because the determinant here means the GCD of the minors, right? And if we have a unit matrix inside, we are done already. So I'm really talking too much just to avoid drawing this. So, okay, it is 1, zero alpha, and zero, 1, minus beta, right? What else plays a role here in our decomposition? We have another thing appearing. It's this, right? So this is 1, 1, alpha minus beta, right? Do we know, any guess where I should draw this vector? Yeah, it is on the same plane as this two-dimensional cone defined by these two rays, right? It belongs on the same plane. So, and it's somewhere in the middle. So let's say this is 1, 1, alpha minus beta, right? Okay, now that's that one. This cone, we know already. It's this one. This cone has this generating function. What about this rational function? Does it correspond to the generating function of some cone? We can see. Yeah. Let's say this is red. This is the cone generated what is this? 0, 1, minus beta. what is the determinant of this? That's 1. So yeah, we're fine with having 1 as the numerator. And this red cone is that cone here, right? Cool. And let's go green here. This one is 1, 0, alpha, 1, 1, alpha minus beta. This is also 1, the determinant, so that's fine. This is a rational generating function of the cone generated by 1, 0, alpha and 1, 1, alpha minus beta, which is this cone here, right? Okay, so what Brion says is take a cone, a two-dimensional cone in 3D, right? And decompose it by taking a vector in the middle of that cone. And then do inclusion-exclusion, right? You decompose, but the intersection is counted twice, so just remove it once more. Okay? Yeah?
I got a little lost. So how are you computing this determinant? You have these 3x2 matrices?
And it's the GCD of the minors. So this would be
The GCD of the minors.
I hope it is 1. Yeah, it is 1 because of this, right? So, and we have another one. So, yeah. That's the geometry of Elliott's decomposition. Actually, this example is enough to trigger some people like me to treat partial fraction decompositions as decomposition of cones, right? What you have to check is that your numerator is really enumerating the fundamental parallelepiped of what the potential generators of the cone would generate. But the moment it happens, yeah, you can see it as a cone decomposition. By the way, what would this recursive algorithm of Elliott do? So then, if this red cone, these are both below 0 in terms of lambda, so we can just forget about it, right? We're sure that it will not contribute a positive or a 0 term. So we forget about it, and let's go again. We do the same decomposition. Essentially, we find again such a thing. Now this is gone, and this happens until we're either at 0 or at a positive part, and we're done. How much time do I have? Okay, I don't have time, so my comment is brilliant with terrible complexity, because as you can see, this cuts at 2 every time, which means what we do is binary search, which means this has terrible complexity. It's a binary, it's a exponential complexity, it's 2 to the something, it's bad. We will see better ways to do this. The first one being the partition analysis implementation of Andrews, Paule, Risse, where we have a better decomposition. So partition analysis is about getting better partial fraction decompositions, and we will see, and we will interpret them geometrically until we have enough insight to say, okay, I don't care anymore about how this is done, because I can do the decomposition geometrically. Thanks.